All right, and welcome back to the last part on proactive cap detection, where I'm going to give you a peek under the hood of this algorithm, tell you a little bit how it works. And I'm also going to talk to you about the prerequisites, and I'm going to tell you about the computational resources that are needed to run this algorithm. Okay, let's dive in. Proactive cap detection under the hood. Well, let me start by referring back to last week, where we discussed this trend prediction model. This was a very powerful model that could take into account periodic behaviors and all kinds of complicated dependencies. Now, keeping in memory such a model for every parameter and constantly updating that model is not really a direction you want to take, as it would require a lot of resources on your system. So instead, what we did is we developed a new lightweight prediction model. This lightweight prediction model can be updated in real time with any incoming parameter change, and it is specifically designed to predict potential breaches of forbidden thresholds. Now, unfortunately though, it is less sophisticated than the full prediction model that we discussed last week. Hence, it's a bit over-eager in the sense that it predicts issues that are sometimes not there. So how did we address this problem? Well, whenever a parameter change comes in, we're going to update the light model first. If this does not detect an issue, then okay, that's it. We wait until the next parameter change comes in. If this light model predicts an issue though, then we're going to train our full prediction model, the one we discussed last week. Now, this full prediction model may or may not detect an issue. If it doesn't detect an issue, we do nothing. But if it does detect a crossing of a forbidden threshold, well then, and only then, will we trigger a suggestion event. Okay, so that is in a nutshell how the proactive cap detection algorithm works. Let me conclude this video by some prerequisites and computational resource information. First of all, prerequisites, you don't need a lot. Proactive cap detection requires a data miner version of 10.1 or higher, and it needs trend data, so you will need a Cassandra or Stas. You can easily enable or disable the feature, as you can with all of our features, through the System Center in Cube. And you can also change the minimal alarm severity that is taken into account to define the forbidden thresholds. We've talked about this in the video before the previous video. What about resources? Well, computational resources are ignorable, but there is something to be said about the memory usage of this feature. To explain that, let me just say a few words first about another of our features called behavioral anomaly detection. Tobe is going to talk about that next week. Behavioral anomaly detection is a very crucial feature. It will help you to detect subtle changes in behavior, and so it can help you to detect issues before they happen. Behavioral anomaly detection is also used in relation learning to automatically learn relations between different components and parameters in your network. So this is a very crucial feature. The flip side, however, is that this is the feature that uses the most memory of all of our features. To be absolutely certain that we don't jeopardize any of your systems, we restrict the amount of parameters that have anomaly detection on. We restrict that number of parameters to 100,000 per DMA, which amounts to at most 2 gigabytes of RAM that is being used per DMA. Now, the proactive cap detection functionality was implemented in such a way that it reuses a lot of the memory that is taken by the behavioral anomaly detection. And that's why running proactive cap detection will only use at most 500 megabyte. And this is really the worst fictional case scenario. In reality, I think it should only use 100 megabyte at the most. That's in real life, because proactive cap detection automatically ignores any parameters that do not have ranges in the connector or that do not have alarm thresholds specified. Okay, so in a nutshell, proactive cap detection doesn't use a lot of computational resources. It does use a lot of computational resources if you switch off behavioral anomaly detection. All right, and with this, I think it's time to wrap up this session. If you want more information, feel free to check out these links. You have the reference in our docs, yeah. You have a nice video on intelligent fault detection on the following link. And of course, if you want to discuss this with us, if you want more information, contact us at ai@skyline.be. All right, looking forward to seeing you again next time, although next time it will be Tobe who will discuss anomaly detection with you. So I'm sure you will be in very good hands. I will come back after that to explain you all there is to know about pattern matching. See you then.